Sine theta and r equals a half. So let's clear this, right? 29. 29 is 1 minus sine theta and r equals a half. Oh, okay. So do we need to do this one then?
Yeah.
Okay, let's still do it. Yeah, go ahead. What's your question, Lena? Yeah, yeah?
We have to
No.
draw a picture by hand?
No, you
Okay.
do not. So if I graph this, I get, ooh, pretty. Pretty so far. And there it is. That's nice. Oh, so pretty. Okay. So you have to be careful that you find the right part of this. This is the area inside the cardioid and outside the circle. So which area are we talking about here? Yeah, like this thing right here. Correct? Now why am I only shading half of it? Why do you only need half of it? Yeah, you could do the whole thing, do it by 2, exactly. So what was that formula we had? We had it was 1/2 alpha to beta of f theta what? Squared d theta, correct? So we have two functions here, so it's going to be 1/2. What's our alpha to beta going to be on this one? Well, let's leave it. Let's do that last, because what did I say the most common thing people do wrong on this is? Yeah. What's the outer radius? The cardioid, so 1 minus sine theta squared. What's the inner radius? 1/2 squared d theta. So we have to do this. So that's going to be half of it. So we're going to multiply. So if we want to do this half of it, we just want to do the green region. What do we have to do to this whole thing? Multiply by 2. So we're going to multiply the whole thing by 2. But now we have to find alpha and beta. We can go from down. So what angle measure is straight down like that? 3 pi over 2. You could do 3 pi over 2, absolutely. So we could say alpha is 3 pi over 2. How do we go about finding beta? Yeah, so you have to find the intersection point, exactly. So you're going to set 1/2 equal to 1 minus sine theta. So what does sine theta have to be? 1/2. So you have to remember the sine of what is 1/2? The sine of what is 1/2? Pi over what? Is it pi over 6? That should be about, how can you visually get an idea if it's pi over 6? How do you know it's visually like that? This angle measure, does it look like it's pi over 6? It does. So now you have this big thing right here. So you have 2 times, well actually 2 and the 1/2 get rid of each other, right? So what does this turn into? Negative, well, no, we decided it was 3 pi over 2, right? 3 pi over 2 to pi over 6 of 1 minus sine theta squared minus 1/4 d theta. At this point, do we actually have an integral we could integrate? Sure. If you didn't have a calculator, you might be pretty sad, because does that look like a nice thing to integrate? Not really. You're almost certainly going to have to use what? Parts. Do you want to use parts? Not really. If this is a calculator part of your test, you'd get to hear on what would you use? You'd use your calculator, yeah. You can use your calculator. You'd have to use your calculator. Yeah, so did you do something wrong? Why? What does this mean? It means that sine of theta is equal to what? Y over the square root of x squared plus y squared. So for which triangle is that going to be true? Which point do I need to anchor the triangle to? Anybody want to guess? A, B, C, or D? A. Let's try A. So if we tried A here, A is the coordinate in rectangular and x, y, correct? Theta right here, if that's theta, we know that this is x and we know that's y. So, and we know what's the distance from the origin to A? The square root of x squared plus y squared. So what is the sine of theta going to be? Sine is opposite over hypotenuse, so what's the opposite? Y over the square root of x squared plus y squared. Is that what we wanted? Yes, it is. So which one is it? A. Does that make sense? You're just going to disassemble it. Draw triangles. Triangles are awesome. You're in 2 dimensions. Triangles still comfort you. When you move to 3 dimensions or really weird non-Euclidean space, they start confusing you. Challenge here. Why can't we just integrate that thing? By infinity. Right, yeah, it's a challenge. So instead, we rewrite this. Can anybody tell me what we rewrite this into? Do you remember? Well, limit as b, sure. B goes to? Yeah. Try that for me and tell me what happens. Try that for me and tell me what happens. Nice. It does come out to be 1. Now, if you had a calculator, what could you do with your calculator to verify or to firmly believe that the answer is 1? What could you do? You could use the integration function on your calculator, but you can't plug in infinity. What could you plug in instead? You can plug in a big number, and you're going to get a number that gets really, really close to 1. And that gives you strong evidence, at least, to believe that this answer is correct. Okay, that's nice. What about, though, another one? This is an improper integral. Why? Why can't you just integrate that thing? Why can't you integrate that? Just straightforward. Yeah, 2 isn't in the domain. What happens at 2? What is it 2? If you graph that function, if you graphed this function, what would you see at x equals 2? A vertical asymptote, exactly, right. So you do rewrite this as a limit. Can someone rewrite it as a limit for me? The limit of what? Yeah, b to 2. Yeah, x minus 2 to the negative 3 dx. Now here's one quick thing. We're going between 0 and 2, so you're going to be approaching 2 from the what? Oh, it's to the negative 2, thank you. 2 to the, are you going to approach 2 from the left or right? From the left. Remember put the little minus sign right there? Now theoretically, this one is very similar to the one we just did. Theoretically, it's very similar. So if we integrate what's inside, we still have the limit as b goes to 2 to the left of, what is it, negative 1, is it 1? No, it's just negative x minus 2 to the negative 1, right? From 0 to b. So you plug b in, and what do you end up with? You still have the limit outside. You still have the limit outside. Bless you. Negative 1 over b minus 2 minus negative 1 over negative 2. Did I do that right? Did I plug it in okay? Can you help me with that? I think I got it. I think I got all the negative signs. Now, here's a limit you can evaluate. Can anybody tell me what this limit comes out to be? It's the limit as b goes to 2 from the left of that thing. What does it come out to be? Well, we don't really care about this, do we? No, everything comes down to this. Right here. What happens to what's inside the green as you go to 2 from the left? It gets really, really big. So what does this go to? Yeah, you're going from 2 to the left, so it's like 1.99999. When you subtract 2, you get a really small negative number. What's negative 1 divided by a really small negative number? So what does that limit go to? It goes to infinity. So this thing goes to infinity. So what do we say about, does this converge? Does this have a stated answer? No. So what would you say this integral is equal to? You could say divergent, or you could say, boom, it gets infinitely large. Because the top is negative. If you go from 2 to the left, it's smaller than 2, so like 1.99999 minus 2 is negative 0.000001. Negative over negative is A. What's negative over negative? Positive. That's why it's positive. Either way, though, does it converge? Either way, does it converge? No, it doesn't converge. It gets really, really big. It's fascinating to me because this one, what does the graph of this one look like? Looks like this, right? And you're doing this area. What does this one look like right here? It's at x equals 2, right? So this looks like this. So you go from 0, it goes like this. This shape right here, how different is that shape to this shape? Is that shape much different? No. One of them converges and one of them diverges. That shouldn't be too surprising to you because we do things like, does the harmonic series converge? 1 plus a half plus a third plus a fourth plus, does that converge? No. But does 1/2 plus a fourth plus an eighth plus a 16th, does that converge? Yeah, so small differences make it converge or diverge. Very small differences. So let's just round it out here. What's the issue with this one? What do you think the most common way, quiz question, what do you think the most common ways to do that one wrong? What do you think the most common ways to do that one? But C approaches what? 0 from the right side from what to what? C to 2. Yeah. Now, you just have 2 of them here. You just have 2 of them. That's nice. Okay. Everybody on this, so Emily over, you do the one on the left. And then everybody else, do the one on the right. Evaluate. Really?
Yeah.
You could plug in 0? How did you do that?
Very carefully.
No. Okay, hold on. No. Look, you have the limit as c goes to 0 from the right. If you integrate this thing, what do you get? Negative 1/3 x to the negative 1/3, and you're going from c to 2, right? So you have negative limit as c goes to 0 from the right of negative 1/3. You're plugging, so it's 1/3. We can pull this out, right, if we wanted to, just like that. 1/8, like that. Oh, not negative, correct? Just 1/8. Minus what? 1/. Can you plug in 0? No, you can't. You can't. What does this go to? Well, this goes to if you plug in something going from 0 from the right, this whole thing, what's this going to go to? Negative infinity. So it's negative 1/3 times negative infinity. So what does this whole thing go to? Positive infinity. Now, this one goes to infinity, that one goes to infinity. So if you add them together, does it really diverge? Yeah. Someone asked in my last class, if you just did 1/2, it's not at this side and it goes to infinity, you have to test the other one. What do you think? If you have this picture, if you know that this blows up, do you have to test the other one? But if you have this picture, what does this picture tell you? Is this above or below the x-axis? It's above. So if you know that this blows up, are you adding or subtracting something when you have this side? Adding. If you're adding something to something blowing up, what's it going to do? It's going to blow up. Now, what happens if one was above and one was below? That's a totally different question. And yes, you have to do both sides. You absolutely have to do both sides. But in this case, they're both going up. One's blowing up, the other one's adding to it. Even if it's convergent, what about the whole thing? It's still divergent. It's still divergent. Absolutely. Okay, so the last. Yeah, you can move the pieces around. What was the purpose of moving the pieces around? Like maybe you've done something like this. If you know that this is true, you know that dy over 100 minus y is equal to dt. What was the point of moving the pieces around like that? Ah, exactly. So if we integrated that, what does that allow us to find? Y in terms of t. That's called finding the solution to a differential equation. When we integrate, what's going to be tacked onto the outside? Plus c, a constant. When you integrate something, how many different integrals are there? A lot. There's a lot of them, an infinite number, right? Do you remember the field thing you had fun with in EV calculus? It was called a what field? A slope field? It's like ocean current. Little tick marks, right? They represent all of the possible solutions to a differential equation. To translate, they represent all of the integrals to some function. This is just a function, right? You can integrate it. That's a visual representation of some current. If you wanted to find a particular solution, you have to have a starting point. You have to have an anchor point, an initial condition. We will be playing around with that. And tonight, you'll be doing some improper integrals, but you'll also be kind of re-remembering what a differential equation is. Okay, sit down and clear your desk, please. Actually, no, let's do our picture first.